There we are. Okay, good to see you guys here. Today I want to do a few things. I want to get you a little bit more practice with limits and just kind of trying to make sure we're really comfortable with the concept behind the limit. And I also want to prove for you that sine 1 over x could not possibly have a limit at 0. So the proof of that is going to be a little bit involved, but I think it's a good thing for us to play with. So that's going to be our little roadmap today. It's not going to be a super involved class. I do want to also talk a bit about the homework. I'm going to extend your first homework because normally the way I do this is today I would teach 2.3 and then next week I would cover 2.4. Instead, today we're going to do 2.4 and Yiping is going to teach 2.3 on Monday of next week. Unfortunately, that conflicts a little bit with the way I designed the first homework set. The first homework set does have problems from 2.3 in it. So I'm going to extend again that first homework set to be due next Wednesday. That way we can learn 2.3 from Yiping student teaching on Monday. And then everything will kind of fall back into order. We'll just sneak 2.4 in here today instead. Oh. So let me swap over. Courses. Section LH1 California Honors. Today is 8/27/21. We're doing today. Get a little bit more practice with limits. We're going to talk about section 2.4 on the precise definition. And within here, I'm going to prove that the function f of x equals sine of 1 over x has no limit as x goes to 0. And we'll also, prove a few limits that are in the positive case.
Professor John, I only can see you. I cannot see the paper.
Oh, goodness me, I'm sorry. I just got to turn on the screen share. Here we go. All right, sorry. We haven't started doing any actual work yet, but here's what we're going to do, right? So we're going to do some more practice with limits from the perspective of section 2.2. Then we're going to go over section 2.4, the precise definition of a limit. This is kind of where we left off on Wednesday. We're going to prove that that function sine of 1 over x has no limit as x goes to 0. And then we'll prove some functions do have limits. All right, so we'll work with some nice easy functions using that rigorous definition. I think before we dive into any of that, we should just get a little bit more practice with the basic results here. Although I suppose we did a pretty thorough job of this yesterday. Let me just take a look at your textbook in 2.2 and make sure I haven't missed anything, any silly details that we want to make sure we cover. I suppose we should look at these. Okay. That's still 2.2, right? All right. Last time we got limits from graphs.
Professor John, your microphone is not clear.
I don't.
I'm having
do about you having problems hearing me?
Yeah, your voice just sounds a little bit kind of foggy, vague almost, but in an auditory sense.
Very weird. The directional mic, I can kind of turn it over this way a little bit.
That's already a little better.
Okay, let's try that. So last time when we were finding limits, we got them from the graph, right? Each time we calculated a limit, we looked at the graph of a function and said, okay, as I approach from the left or approach from the right, my y values are getting closer and closer to this particular y value. Today, so curve like this, y value over here like this. And we said that, because we can imagine sneaking up on this x value from the left or the right, and in either case, the y value of our little dude as he sneaks up there is getting closer and closer to this horizontal line y equals L. We'd say something like, because the limit as x approaches c from the left of f of x equals L, and that is also equal to the limit as x approaches c from the right of f of x, the overall limit when x approaches c of f of x exists and is equal to L. All right, this was kind of the basic result last time. Sneak up from the left, sneak up from the right. If the behavior is the same, I don't really care what happens at that point. I just care about what happens nearby. As long as those behaviors from either side are the same, then we say the overall limit exists and is equal to L. First today, I want to practice working limits without graphs. And Yiping is going to talk a lot more about this stuff on Monday, but I just want to show you one or two examples where maybe it looks like we can't calculate a limit at first, but we can get there. So the kind of classic example here, stuff like this. As we will see in the future, oftentimes when you're trying to calculate a limit algebraically, the first thing you should do is just try to plug the number in. But if you try to just plug 1 in here, you get into trouble. Because the downstairs would become 0. But what I can do is a bit of algebra. If I factor the top, we can think of that bottom as x minus 1 times 1, and then cancel, cancel. And we get this, into which we can plug x equals 1. We just get 2. Or you could think about it as coming from the graph again. The graph of this function, f of x equals x squared minus 1 over x minus 1, looks like this. And I know it looks like this precisely because of the algebra I did over there. And so again, you could argue graphically, if I sneak up on this point from the left or from the right, my y values will be getting closer and closer to 2. You've seen this in pre-calculus. If you have a rational function where there is a factor common to the top and bottom, once you cancel those factors, this kind of hole goes away. And before you cancel the factors, you have a graph of a function who has a hole at the x value wherever this bottom factor that gets canceled happens to be 0. There are some other sort of common algebra tricks like these. So factoring, definitely. Factoring the top and bottom and seeing if you can cancel a factor is a very useful trick. Kind of related to that, something that, that you'll see more of with Yiping's lecture is a multiply by the conjugate sort of trick. So here, if I tried to send t to 0, you see the bottom is going to 0, and so is the top, right? The top is going to go to the square root of 9 minus 3. In this particular example, they're just plugging in values. They're plugging in values of t that get closer and closer to 0 and looking for patterns. That is a workable approach, but it's not a pleasant one. So here's what I would advise for something like this is that you multiply by a conjugate. Let me see, do they actually do this here? Let me just work you through it. Yeah, so I end up saying this is a little bit misleading. So another trick is to multiply by the conjugate. Now, in the context of complex numbers, by conjugate, we mean the complex conjugate. Like the complex conjugate of 1 minus 3i is 1 plus 3i. You can use that terminology for expressions like these too. So like the conjugate of t squared, the square root of t squared plus 9 minus 3 would be the square root of t squared plus 9 plus 3. So let's see if we can do this. You see the same problem. If I plug in 0 for t, the bottom goes to 0. The top also goes to 0, but that doesn't help me. The bottom being 0 means I really can't work with that. But if I have this clever insight to multiply by the conjugate, which is the square root of t squared plus 9 plus 3, and if I'm going to multiply by that upstairs, I got to multiply by that downstairs. If I do this and then kind of distribute everything out, right, being mindful that fractions always have their tops and bottoms in parentheses, just a fact of algebra. If you FOIL out the top, you'll have square root t squared plus 9 times square root t squared plus 9, which is square root t squared plus 9 all squared, plus 3 square root t squared plus 9 minus 3 square root t squared plus 9, and those middle terms will eat each other up, and then minus 9, 3 times negative 3. And then downstairs you have t squared times the square root of t squared plus 9 plus 3. So this is a classic trick that you will see more of when you talk about limit laws. Also, this piece here, the square root of t squared plus 9, when you square it, just becomes t squared plus 9. So your numerator here is t squared plus 9 minus 9. So you just have t squared over t squared times the square root of t squared plus 9 plus 3. And the t squareds can be canceled. because there is a factor of t squared upstairs and a factor of t squared downstairs. And that brings us here. Then t to 0, 1 over the square root of t squared plus 9 plus 3. And technically, we don't know how to calculate this limit yet. The last problem, when I got to this step, I know what the graph of that function looks like. I know what the graph of x plus 1 looks like. The graph of this function is a little bit complicated. It's not something that I would expect you to know. But once we have our basic limit laws on Monday, you'll know how to take this limit. And it is the thing that you would hope it is. You just plug in 0 for t. The magic of all this algebra that we did is that we're able to get rid of the factor that made the denominator 0 when t went to 0. So you could just plug in 0 for t here and you get the value of the limit out as 1/6. But the point is to just introduce these algebra tricks, factoring and canceling, multiplying by the conjugate. Okay.
But we would still, when we're actually graphing it, we would be graphing it with an empty circle to mark the spot where x would still equal 0 because of the original function that we started with.
So the original function would have a hole at t equals 0, but this function does not have a hole at t equals.
So at the end, when we do learn how to graph this, we would be graphing the final function that we just got here, or are we graphing the original one based off of the information we're getting from this final one?
Neither, really. So the way we would solve this problem from this stage is to apply our limit laws and send t to 0, just plugging it in. So we wouldn't, on a problem like this, we wouldn't ever lean on the graph. The graph of a function like this is a little bit complicated. It's not an easy thing to graph. I will give you some techniques later in the course that would hypothetically allow you to graph this, but you don't want to need to do the graph in order to get the limit. So what you're going to learn from Yiping on Monday is that under a certain set of conditions, you can just calculate a limit by plugging in. And that's the way we would actually arrive at our result here, is by doing this algebra to get to a more or less equivalent form where we can plug in 0 for t.
Oh, okay, perfect, thank you.
So no way along the process would we actually need the graph, which is nice. Let me make sure I'm not missing anything else in 2.2. We want to show you these algebra tricks. Can make some tables. I'm not going to do that. Yeah, so that brings us to here. Okay. So last time I made the claim that sine of 1 over x has no limit at 0 because the graph oscillates too quickly. Recall the definition. We say that lim x to c of f of x is equal to L, provided for every positive number epsilon, we can find a positive number delta such that if x minus c has absolute values smaller than delta, then f of x minus L is guaranteed to have absolute values smaller than epsilon. And this is kind of our grown-up version of saying the left and right limits are equal, right? This is the way we define what a limit is. I would like to use that to prove that this has no limit at 0. So we're going to prove claim? And I would say first, observe that the range of sine 1 over x is the closed interval from -1 to 1. So if the limit as x goes to 0 of sine 1 over x does exist and is equal to L, then L has to be an element of the interval -1 to 1. Right? A function whose range is -1 to 1 can't have a limit that's like 2 or 5 or something like that. You got to sneak up on whatever your limit is. It doesn't necessarily need to be an element of your range, but it needs to be an element of the closure of your range. And since the range here is a closed interval, the limit has to come from that. All right. Let me remind you what the graph of sine 1 over x looks like. Let's see, I guess I can draw it. Oh, no, I won't do that here. So the kind of reason why this isn't going to work is because we'll be able to specify an epsilon for which no delta can be found. Right? This says for every epsilon, we can find a delta such that blah, blah, blah. We are going to specify a particular epsilon and say that no matter what delta is, this cannot be true for that particular epsilon, because as x gets closer and closer to 0, I will be able to make this thing larger than epsilon. Does that make sense? All right. Suppose L is greater than 0. Right? And then you could work through this separately where L is smaller than 0. That means that the limit of our function is some positive number. Right? And this is a picture that you could flip over and it would work fine. I'll just say L is right here. All right. Bigger than 0. Maybe it's equal to 1 itself. Doesn't matter as long as we're just assuming larger than 0. You know that somewhere out here, this function comes in and it starts bouncing back and forth. 1 to -1, 1 to -1. And it does this pretty quickly. What you would need to show is that given any epsilon window about L, once my x values get close to 0, the y values get trapped in this epsilon window. So let me draw the L in. That's what we need to see in order for the limit to exist and to equal L. Now we know that that's not going to happen, or at least if you trust me, you know that that's not going to happen. I'm not going to draw things in here because it gets way, way, way too cluttered. But your delta window has to look something like this. The definition says that if the limit as x goes to 0 of sine 1 over x is equal to L, then for all epsilon greater than 0, we can find a delta greater than 0 such that, and now I'm just going to plug in the C's and the L's and stuff. So absolute value of x minus c is less than delta, that would just be absolute value of x minus 0, which is the absolute value of x is less than delta. Implies that the absolute value of sine 1 over x minus L is less than epsilon. If epsilon is really big, then this isn't a problem. But the idea is that this should work even for epsilons very, very small. In particular, if I take epsilon to be something like 1/2, then this is 1/2, this is 1/2. And you'll see that this function is bouncing back and forth really, really quickly. I need to be a little bit more careful though. In order to, so the way I'm going to do this is I'm going to show you that this function actually has infinitely many x-intercepts on this purple delta window down here. That's going to be the game. So I'll show that you can't stay close to L because you have to hit this x-axis infinitely many times as you get closer and closer to 0. And that will contradict this definition. Now again, like I said, we need to take a particular epsilon and show that for that particular epsilon, there is no delta which works. In order to say this epsilon window isn't going to come all the way down to the x-axis, I need to take epsilon strictly smaller than L for sure. I could take it smaller than L over 2. That would do the job because L over 2 is right here. And that puts some space between my epsilon window and the x-axis. So in particular, if we take epsilon equal to L over 2 and observe that sine 1 over x is equal to 0 whenever x is equal to 1 over n pi, we will see that no matter how small we choose delta, the sine of 1 over n pi minus L will be greater than epsilon for infinitely many n. Right, this is the idea. So sine of sorry. Let me just write this as sine of 1 over x. This will be a little bit easier to digest, I think. How small we choose delta, sine of this and this, despite absolute value of x being less than delta. All right. So this would contradict this, right? If saying no matter how small you choose delta, even if x minus c is less than delta, the absolute value of f of x minus L is going to be bigger than epsilon. Why? Well, like I said, I'm going to take epsilon to be L over 2. And then I'm going to say that on any interval of the form absolute value x is less than delta, I have infinitely many things like this. Now, why why is it the case that sine of 1 over x is equal to 0 and x is equal to 1 over n pi? Well, because when you plug in 1 over n pi here, you get sine of n pi, which is always 0. So again, let me draw one more little picture here for you before we try to dive in and unpack everything.
Professor John, will this show in the exam?
There will be qualitative questions about this sort of thing on the test, but probably not any quantitative questions about this sort of thing on the test. So I may ask you to prove that some limits exist or some limits don't exist, but they won't be as hard to argue or as complicated as this. All right. So here's my 1 over n pi. And I know that my graph is going to be down here at 0. Because sine of 1 over n pi is 0. Here is L. And then epsilon is L over 2. So it's half the distance from L back to the x-axis. This is L plus epsilon, and this is L minus epsilon. So what we're supposed to see is that anytime my x's are within this purple window, my y's stay within the blue window. That's what that's supposed to say. So when we say absolute value of x less than delta implies absolute value of sine 1 over x minus L is less than epsilon, this means if x is in the purple interval, the negative delta to delta interval, then the y value on the graph is in the epsilon window about L. All right. So in terms of the picture here, I think you can see that that's not true, right? The graph gets very, very cluttered in here. So rather than trying to draw the whole graph, I just want to draw your attention that here's a point, an x value. It's of the form 1 over n pi. No matter how small you choose delta, I can make n large enough so that 1 over n pi is inside this interval. Does everybody understand why? As n gets bigger and bigger and bigger, 1 over n pi gets very, very, very small. Since sine of 1 over x is always 0 when x is anything of the form 1 over n pi, I know that there is at least one x-intercept in here. The truth is that there's infinitely many x-intercepts in here, but there's at least one. And I can find one of them that is smaller than delta. So the graph of the function sine 1 over x, everywhere inside this little rectangle, right? Anytime the x's come from this purple region, the y's need to be trapped inside the blue region. But I have found a point that I know is on the graph, 1 over n pi comma 0, which is also outside the blue region, which contradicts this definition. That's it. That's the proof. How do we feel about this? Remember, the idea is the shrinking epsilon window should force a shrinking delta window. As the epsilon window shrinks, your delta window should be able to shrink along with it such that the graph of the function is contained within this rectangle created by the epsilon and delta windows. What we've done is said no matter what L is, as this epsilon window shrinks, I can find a point outside of this rectangle. So no matter how you try to shrink the delta portion down, there will always be a point outside of that epsilon window, right? Even if you try to bring this purple in, I can find another point of the form 1 over n pi that's within that purple, and thus an x-intercept that brings us out of this blue epsilon window.
Would it be possible to do an example where it doesn't contradict the definition, just so I can see like what it's supposed to look like?
Yeah, absolutely. We'll do a positive example next. We'll do a few fairly straightforward ones.
Thank you.
All right. So the take home here is that lim x to 0 sine 1 over x does not exist. We did assume at the start that L was strictly positive. If you assume that L is strictly negative, you can mirror this argument. And if you show that if you assume that L is 0, you can just find infinitely many points where your graph bumps up to 1. So the argument really is complete here. This is a without loss of generality thing. And I encourage you to take the time to really think it over. But yeah, let's look at some positive examples, right? And let's start nice and simple. Let's prove that the limit as x goes to 3 of 2x is equal to 6. Indeed, David, there are infinitely many points where y will be all the way down here at -1 also. It's just kind of easiest or most convenient to find these. But yeah, that's the idea, is that the graph oscillates really, really fast, like infinitely often, all the way from -1 to +1 on any interval containing 0. So not only is there some point where y will be -1, there's infinitely many. All right, so here's my f of x. Here's my L, and here's my C. So if I want to try to plug these into the definition, we would say that that definition says for every epsilon greater than 0, we can find delta greater than 0 such that abs x minus c less than delta implies abs f of x minus L is less than epsilon. In practice, what you do is you usually start with this and kind of work backwards to find your delta. All right, so here's how we do this proof. Let epsilon greater than 0 be given. It's an arbitrary positive number. And then I'm going to find the delta depending on epsilon that works. Then the absolute value of f of x minus L less than epsilon, just plugging things in now, is the absolute value of 2x minus 6 is less than epsilon. Remember what my goal is. My goal is to find a bound on x minus c, which is a bound on x minus 3. So what we want to do is try to make x minus c show up here somewhere. And that's not hard. If you factor out a 2, you get this. And then if you divide both sides by 2, you get this. So what we see is that if x minus 3 is less than epsilon over 2, then 2x minus 6 will be less than epsilon. Those are logically equivalent. Therefore, we can take delta to be epsilon over 2. Then, if absolute value of x minus 3 is less than delta, that's the same as saying absolute x minus 3 is less than epsilon over 2, which is the same as saying 2 abs x minus 3 is less than epsilon, which is the same as saying 2x minus 6 is less than epsilon. So anytime your absolute value of x minus 3 is less than this particular choice of delta, right, and delta is allowed to depend on epsilon, you will be guaranteed that the absolute value of 2 minus 6 is less than epsilon. Not bad at all, right? The absolute value of f of x minus L is less than epsilon as desired. And that's the proof. So in the positive case, this is what it looks like. Some ways that this can get weird or difficult, of course, here we're dealing with a linear function. Even as soon as you go to prove that quadratic functions have nice limits that are easy to calculate, the algebra gets a little bit gnarly. But there are other examples we can look at. Let me take a look at your book. So there's sort of fun things we can play with here. That's 2, 3. Now we want 2, 4. So something fun. Yeah, this is like what we just did. These are easy. These are easy. These are fun. Yeah, proving the sum law and stuff, but it wouldn't be appropriate to do that now. Let's do this one. This one's not too bad. The trick here is going to be the choice of delta. It's not super obvious. Yeah, this is 2.4. This is section 2.4. Maybe there would be something that doesn't involve such a weird choice. Yeah, showing this delta works. It is. It's wonky. I'll prove that for you later. Let's take something that looks a little bit more fun. Prove the statement using delta epsilon definitions. Those are all still linear. 25 might be fun. Yeah, I may ask you to prove some fairly simple limit work on tests, but I'm not gonna push you too hard. Let's take a look at number 25. This will be the last explicit example that I do like this, at least for today. I'll work more with this definition after we have the limit laws. We'll prove them. So let's see if we can prove that the limit x goes to 0 of x squared is itself equal to 0. So here, c is 0, f of x is x squared, and L is 0. Means we want to show that for every positive number epsilon, there exists a positive number delta such that if the absolute value of x is less than delta, then the absolute value of x squared will be less than epsilon.
What's the first sentence written? You have f of x equals x squared and L equals 0, and what's above those? What does that say?
C equals 0, f of x equals x squared, and L equals 0.
Okay.
Yeah, so this up here, this is a lowercase c. C f of x. L. All right, so here's the statement, right? This is what we need to show. We need to show that given any positive number epsilon, there exists another positive number delta, such that whenever x is absolute value is smaller than delta, f of x's absolute value will be smaller than epsilon. One way to handle these sort of things, again, you always kind of want to work backwards. You start with this, and then you sort of try to reduce it to a statement that looks like this. So proof. Again, let epsilon greater than 0 be given. We seek delta. If the absolute value of x squared is going to be less than epsilon, that's the same thing. Here's some just rules for absolute values. That's the same thing as saying the absolute value of x squared is less than epsilon. Now, since epsilon is a positive number, I can take square roots here. And this is the same as saying that the absolute value of x is less than the square root of epsilon. And now this looks an awful lot like this. So we can take delta to be the positive square root of epsilon. This implies that whenever x is less than delta, that's the same as saying the absolute value of x is less than the square root of epsilon, which is the same as saying the absolute value of x squared like this is less than epsilon, which is the same as saying the absolute value of x squared is less than epsilon. And that's what we wanted to show. So again, we're done. This is how analysis proofs kind of always go, and it takes some getting used to. There's a famous mathematician named Paul Halmush who said that he didn't understand epsilonic analysis till his second year of graduate school, which is a little bit sad, a little bit slow there. But you always begin with an arbitrary positive number epsilon. And then you're always looking for something else, usually depending upon epsilon. So what we want to do is say, God hands me some number epsilon. I want this to be true. What choices for delta will allow this implication to be true? So anytime x is smaller than delta, x squared would be smaller than epsilon. Oh, well, clearly, if you take delta to be the square root of epsilon, then if x is smaller than the square root of epsilon, x squared will be smaller than epsilon itself. The logic that you have, the actual steps of reasoning you need to take are not that hard. The challenge is in kind of understanding the workflow, how the different things connect to one another. This is not in your current homework set because originally I planned to do 2.3 today and then 2.4 on Monday. So these will be in your homework set for next week. But this is a nice example where I can draw you a picture and I think it'll help. All right, here's the squaring function. And what we want to say is that given some epsilon window about L here is 0, so the L plus epsilon would be this, and L minus epsilon would be this. I want to say, in order to stay within this window, how far does x need to be from 0? Well, you can see it right here, right? As long as I stay within this delta window, the y values on my graph will stay within that epsilon window. In other words, I found a rectangle whose width, delta, depends on epsilon and guarantees that the graph stays inside. And the choice of delta that works here is the square root of epsilon. All right.
So I'm understanding it visually very much, but when you get to all of the letters, I'm just having a very hard time breaking down the meaning of every time you go for the such that. I completely loses me.
Let me try then see if we can try one more that has a kind of nice smooth feel to it.
Thank you.
What would be good? What of a constant's a constant? That's not especially exciting. Verify. That's how I do that. No. Yeah, I think this would be good. Let's take a look at number 36. So there we're asked to prove that the limit as x goes to 2 of 1 over x is 1/2. All right, so what do I want to show? Is that for any epsilon positive, I can find a positive number delta such that if the absolute value of x minus 2 is less than delta, then the absolute value of 1 over x minus 1/2 will be less than epsilon. That's what I want to show. So try and parse the such that here before we do anything else. Such that really just means under these conditions. Right, so I'm trying to find a delta which guarantees if the absolute value of x minus 2 is less than delta, then the absolute value of 1 over x minus 1/2 is less than epsilon.
Wait, but how do you get the absolute value of x minus 2? Like, why would you choose that?
Well, this is just from the definition, right? The definition says absolute value x minus c less than delta implies absolute value f of x minus L less than epsilon. So each of those individual pieces is coming from the definition itself. And if we look at the picture, I'll just draw the first quadrant. One over x looks something like this in the first quadrant. Maybe 2 is over here. And this function is nice and continuous as long as we stay away from 0. So what I'm trying to do is say, okay, here's 1/2 plus epsilon. Here's 1/2 minus epsilon. I want to stay within this window. I want to find the deltas that keep me within this window. So visually, I can find them, right? The lower bound for delta would be like right here. And the upper bound for delta would be somewhere over here. I can see visually that as long as I'm coming from this purple interval, the graph will stay inside this rectangle.
And we do this by choosing an arbitrary positive value, in this case 0 for epsilon, and then solving that one. And then what are we doing with the delta side?
Well, we can't use 0 for epsilon. Remember, epsilon has to be a positive number. The idea is that epsilon is usually a very, very small positive number. But what we are going to do is we're going to work with this inequality and try to rearrange it into something that looks like absolute value of x minus 2 is less than some stuff. And then that stuff will be our choice for delta. So kind of if you look back at each of the last few examples, I begin with this statement, and then I work with it algebraically until I'm able to get something whose left-hand side looks like this. Does that make sense?
Yeah, that actually really does.
Good, good,
We're
good.
just getting so that we can look at them in similar terms, or compare them to each other, frankly.
Yeah, that's the vibe. So
Okay, cool.
the absolute value of 1 over x minus 1/2. I can rewrite, let me do it the way I was doing it before. We'll be consistent with our notation. Absolute value of 1 over x minus 1/2 is less than epsilon. Says the same thing as, I'm just going to have a common denominator in there. This is going to be absolute value of 2 minus x over 2x is less than epsilon, which is the same thing as the absolute value of 2 minus x over the absolute value of 2x is less than epsilon. And that's the same thing as, I'm going to do two things here. First, the absolute value of 2 minus x is the same as the absolute value of x minus 2. And then I can multiply over by the 2x. So I get epsilon times 2x. Now, what I don't want is my delta to depend on x. Delta is allowed to depend on epsilon, but it's not allowed to depend on x. So here's my absolute value of x minus c. This is looking good. What I want to do now is imagine where I'm sending x. I'm sending x to be very, very close to 2. So 2x should be very, very close to 4. And what I would like to check is if I have delta equal to 4 epsilon, do I have the original inequality? Will that be guaranteed? In other words, how big could this 2x be? Oh yeah, David, I'm sorry about that. I'll try to pull my hand away for a good period of time after each little discussion there. So how much could this term hurt? I should still have an absolute value here.
I mean, according to the visual graph, not much.
Well, yeah, I'm trying to send x towards 2, right? These x values should themselves be pretty close to 2. So we ask, how large can absolute 2x be? Should be close to the absolute value of 2 times 2, or 4, because we're sending x to 2 in this limit. So maybe we should say that delta is equal to 4 epsilon. Does this work? And if the algebra doesn't come out really nicely, I could always take delta to be just something smaller, like 3 epsilon, 2 epsilon, or even epsilon itself. So let's try it. is it true that if the absolute value of x minus 2 is less than for epsilon, then the absolute value of 1 over x minus 1 over 2 will be less than epsilon itself? That's what I want to know. Well, the absolute value of 1 over x minus 1/2 let's see, how do I want to start this? Is indeed equal to the absolute value of 2 minus x over 2x. And that is equal to the absolute value of x minus 2 over absolute value of 2x. So this would be smaller than 4 epsilon over the absolute value of 2x. And then what we need to do is take this piece and try to use it to argue that the absolute value of 2x isn't going to mess this up, right? So we're wondering, is this smaller than epsilon? And I'll say, and since abs x minus 2 is less than 4 epsilon is equivalent to saying negative 4 epsilon is less than x minus 2 is less than positive 4 epsilon, which is itself equivalent to saying 2 minus 4 epsilon is less than x is less than 2 plus 4 epsilon. We can say that 4 minus 8 epsilon is less than 2x is less than 4 plus 8 epsilon. So here, this is just working with absolute value inequalities. I take this inequality and unpack it. This is defined to be this. Then I add 2 everywhere. And then I multiply through by 2. And now what I want to do is try to reinterpret this. I could subtract 4 everywhere and say, now this is the same as saying that negative 8 epsilon is less than 2x minus 4 is less than 8 epsilon, which is equivalent to saying 2x minus 4 is less than 8 epsilon in absolute value. I'm not sure this is super useful though. So because what I really want to do is bound 2x, not 2x minus 4. So instead, let's come from here and ask, okay, so how big and how small can the absolute value of 2x be? Well, if 2x is smaller than 4 plus 8 epsilon and bigger than 4 minus 8 epsilon, the absolute value of 2x would definitely have to be smaller than 4 plus 8 epsilon. Right? And that's going to be enough to do this, because now I know that this piece is only so big. The largest that could possibly be is 4. So this is less than 4 epsilon over 4, which is epsilon itself. And that's exactly what I wanted to prove. I wanted to prove that this piece is smaller than epsilon. So working with these delta epsilon arguments is not the simplest thing in the world, but it's also not the hardest thing in the world. And I think the way to begin is with pictures, right? So what you want to really do every time you see one of these problems, and I will put some of these on your homework for next week. I'm going to post some videos and things for you guys to watch for practice. When you get to some of these problems next week in your homework, and there will be things, you know, mostly like these, begin with the epsilon statement. and try to work backwards to a statement about x minus c. So you begin with your f of x minus L is less than epsilon, and you try to work with it algebraically until you get something that looks like x minus c is less than some stuff. If you're lucky, this stuff over here will be like epsilon times a constant, and then you're done, life is easy. But more often than not, you're gonna have something else that kind of messes things up or makes it a little bit difficult. And in order to grapple with this, you'll have to come to the side and make some sort of separate argument. But things were exactly like we said they were. 2x is bounded above by 4. The absolute value of 2x is bounded above by 4. So this piece is at worst, as long as x is close to epsilon, or sorry, x is close to 2, this piece is at worst epsilon, which is what we wanted. So the choice here of delta equals 4 epsilon does work. Yeah, these are tricky. They are. So I would encourage you to start with linear functions. Start not necessarily with these. Thinking about these pictures will help you a little bit. But then when it comes to actually proving these things, the first functions that are going to be easiest to work with will be linear functions. So if I were you looking for like stuff you could actually practice to help yourself, 15, 16, 17, and 18, those will be the ones that are sort of the easiest. 19 and 20 here are not bad. 21 and 22 are very similar in the sense that you can factor and then you get a linear function. 23, 24, I think you'll also find easy. Where they start getting challenging is 25, because the algebra here that you have to do with the absolute values is a little non-obvious. I think in order to avoid overwhelming you for the day, I won't hit you with any more of this stuff. I think we'll probably stop here for the day. And then on Monday, Yuping is going to teach us how to use the limit laws to calculate limits. So that's going to be section 2.3. And then after she's done that, I will come back and prove these things using the delta epsilon definition. And I think by that time, because you'll have practiced with it a little bit and then done some actual work with limits and the limit laws, things will start to crystallize. So if the delta epsilon stuff is feeling weird, intimidating right now, don't feel bad. That's normal. It really, really is. But as you practice more and more with the theorems surrounding limits and graphs and calculating limits from graphs, I think you'll start to become a bit more accustomed to them. I'll tell you this, the delta epsilon stuff is going to stick around. We are going to continue using it, but I will not always boil things down to first principles. So if there is a proof that I can show you that doesn't require a delta epsilon argument, I'll show you that instead. But there will be different times through the year where we refer back to delta epsilon definitions. So it's worthwhile to spend a little bit of time. I promised that I would find you some resources you can use to help. So here is essentially the proof that I used for the sine 1 over x. So you can review the sine 1 over x argument on stack exchange here. And then this guy I trust to do a good job. So you can see more examples from him. Yeah, stack exchange really is the best. So you can watch him make a few more delta epsilon limit arguments there before getting yourself into a situation you have to try it on your own. Okay, last thing before I let you go, I said this at the start of class, but I haven't actually done it yet, and I want to make sure it's clear. The homework one that I've opened up for you, you're welcome to get in there and try to knock all of that out. But because we decided to change some things around for the student teaching, I'm going to make this homework be due. I need to edit the schedule. I'm going to make this homework be due next Wednesday. So I do trust that everybody could get in there and start working on it now, but when you get to the latter problems where you have to find the limit of f plus g, f minus g, that sort of thing, don't stress. It's true that we have not covered that yet. Yuping will be showing you guys how to do that on Monday, and then you'll have until Wednesday of next week to finish up that homework. Alrighty, any questions for me before I let you guys go?
Professor John,
Yes.
when will you post the YouTube videos? or
As
9?
soon as I can. So the YouTube videos from Wednesday and Monday are already up. The YouTube video from today, I will post as soon as I can. So after I get out of here, I'll start uploading them. Once they're uploaded, I'll post them.
I talk about the class. The last time, the second class and today, the class on today. When will you post in the YouTube? I didn't see the last class on YouTube.
It is there. So if you go to the announcement in Canvas, you'll find that link here. This is the video from Wednesday.
Okay.
And then the video from today, I'll post no later than like 4 p.m. It takes my computer a little bit of time to buffer, and then it takes time to upload. But as soon as I've got it uploading to YouTube, I'll post the link here.
Could you post it in the modules, because that will look more convenient. And also you can type the length lectures, the date, and also can put the information about look like the limited law and the limited this definition, something on the length, so that if I want to find some information, I just see the link, I can create the correct video.
I can see about that. So organizing all of the YouTube videos in that fashion would take a good deal of time. What I can say is this: when I upload these videos, let me show you here my. So I do include a little description, what topics are in there, and I do include the date. That will always be there. So if you were to click on this guy, this loads. We have just the basic topic here, and we have the date here. I can post them to the modules. And then what else is it that you wanted? You want me to post the videos to the modules with a short description, and what else?
That's all. Thank you for right now.
Okay.
For right now that's all.
Alrighty then. Yeah, I'll be happy to do that. No problem.
Thank you so much.
Alrighty. Take care, guys. I'll see you on Monday.
Bye-bye.